Intel's rise began in 1968, eventually establishing the x86 architecture as the primary standard for the global personal computer market. But the last decade has been defined by stagnation. After years of delayed manufacturing transitions, moving from 14 nanometer to 10 nanometer, Intel's market capitalization has settled around $175 billion. To understand the risk Intel is taking, look at the gap between their profits and their spending. Their historical gross margins are falling, yet they are committing to a $100 billion manufacturing pipeline. This financial imbalance is a deliberate bet. They are attempting to reclaim the manufacturing lead by launching 5 process nodes in just 4 years. That entire strategy relies on the physics of a single manufacturing milestone, the successful launch of the 18A process node. Overseeing this transition is CEO Lip-Bu Tan. Appointed in early 2025, Tan is a semiconductor veteran with a mandate to enforce strict balance sheet discipline. The cost of funding the new fabs has been high. Intel has suspended its dividend and moved to lay off approximately 20% of its workforce, a reduction of up to 25,000 positions. To ensure long-term viability, Tan now requires all new products to mathematically demonstrate a 50% gross margin hurdle before they can enter production. These cuts are designed to provide the capital necessary for the IDM 2.0 pivot, transforming Intel into a contract manufacturer capable of taking business from TSMC. But these financial shifts only matter if the engineering team can deliver. Success now depends on logic structures measured at the 1.8 nanometer scale. As transistor channels shrink toward the atomic scale, traditional FinFET designs reach their limit. The gate can't fully contain current, leading to electrical leakage. This is the current industry standard, the FinFET. Intel's 18A process replaces this with RibbonFET. This architecture wraps the gate material completely around the channel, providing 360-degree electrostatic control. This new geometry enables a 30% increase in transistor density and a 15% improvement in performance per watt compared to the previous Intel 3 node. Beyond the transistor itself, 18A introduces PowerVia, the industry's first high-volume implementation of backside power delivery. Typically, power and data signals share the same front-side wires. This causes interference and a drop in voltage known as IR drop. PowerVia solves this by moving the power delivery network to the other side of the wafer, routing it exclusively from the back. By clearing the power lines from the top layer, engineers have more room to optimize data routing, which reduces overall design complexity. Intel began risk production of 18A in April 2025, a timeline allowing them to bring these innovations to market ahead of TSMC's competing N2 node. This technical overhaul is the foundation for Intel's entire 2026 product roadmap. The engineering wins of 18A must now secure commercial design wins, starting with the consumer market. Panther Lake will be the first 18A client processor, targeting an AI PC market that is projected to reach 100 million units by 2027. But the data center is where Intel faces its most significant competitive pressure. To address high-efficiency cloud demand, Intel is launching Clearwater Forest, a Xeon processor built on 18A that uses dense efficiency cores to reduce power consumption. The competition is intense. AMD continues to gain share in the x86 server market, while NVIDIA controls the $40 billion AI data center segment. Intel's Gaudi 3 accelerators provide a cost-effective alternative for AI inference, though they lack the broad software ecosystem of NVIDIA's CUDA. Intel's unique advantage is its IDM 2.0 model. By designing the chips and owning the 18A fabs, they can co-optimize hardware and manufacturing in a way that fabless competitors cannot. Intel is attempting a cultural and operational shift, moving from a focus on its own chips to serving external fabless clients. The current results show the scale of the challenge. In Q3 2025, external foundry revenue was just $35 million, despite billions in capital investment. This creates a margin problem. TSMC averages 60% margins, AMD sits at 53%, but Intel trails at 40%. Geography contributes to this. Building advanced fabs in the US costs 20 to 30% more than Asia due to labor and infrastructure. Furthermore, developing 18A yields compress margins in the short term, as early production runs typically result in fewer working chips per wafer. Intel is competing against TSMC's mature processes, which consistently deliver yields above 90% for established customers. To justify these costs and bridge the margin deficit, Intel is marketing a specific advantage: geographic supply chain security. Increasing geopolitical tension in East Asia has turned global supply chain diversification into an absolute top priority for the entire semiconductor market. The high concentration of advanced manufacturing in Taiwan represents a significant vulnerability for global trade. Intel is positioning itself as the primary alternative, with a manufacturing footprint that spans Arizona, Ohio, New Mexico, and Ireland. These facilities represent some of the most complex industrial investments in Western history. This domestic capacity is anchored by over $20 billion in total support from the U.S. CHIPS Act. This includes a $3 billion federal grant for the Secure Enclave program, ensuring Intel's role in manufacturing chips for sensitive defense and intelligence applications. Intel's expansion shifts their output from standard silicon processors to sovereign supply chain resilience for Western governments and hyperscalers concerned about offshore production. While the 18A node provides the foundation, long-term manufacturing advantages increasingly depend on advanced packaging like EMIB and Foveros 3D stacking. These technologies allow for systems of chips, interconnecting multiple tiles from different manufacturing nodes into a single high-performance package. This shift toward disaggregated designs will drive the roadmap for Intel's future 14A and 10A nodes. To sustain this investment, Intel Foundry must secure 10 to 15 major external clients by 2030 to fill their expanded capacity. The financial objective is to generate $10 to $15 billion in annual revenue from these external foundry services. Success requires Intel to move past its history as a vertically integrated giant and adopt the operational discipline needed to serve as a world-class foundry. By tying its future to the physics of RibbonFET and the security of domestic manufacturing, Intel is attempting to become the essential infrastructure for the next generation of Western technology.